In this video, I'm going to cover Newton's third law and how to identify Newton's third law force pairs. I've written Newton's third law here in a way similar to most books, in that it doesn't really convey any helpful information. Newton's third law is something in popular culture. For every action, there's a reaction, but that really is more misleading than helpful. Newton's third law isn't really useful until you really understand it, and you can identify Newton's third law force pairs correctly, which is what we will be able to do after watching this video. But first, an experiment. I want you to hit something, like a wall. When you hit something, you exerted a force on that object. And maybe you heard a sound, that object vibrating, that was caused by the force you exerted on that object. But you also felt something too. I mean, hopefully you didn't hit it so hard you hurt yourself, but you certainly felt it in your hand. Maybe it stung. That was the force the object exerted on you. You had exerted a force on the object exerted a force on you, and those are Newton's third law force pairs. I'll call them with this acronym N3FP. They're also sometimes called an action-reaction pair. That's a little misleading because action-reaction seems to imply one comes first, and that's not true. Newton's third law force pairs always exist at the same time. Let me take a look closely at what happened. So here's an agent, the red ball, that represents your hand. You hit an object, the blue square, that represent the wall. Remember when we talked about forces, every force has to have an agent and an object. That comes into play here, even though before we were always worried about just the object. In this case, the agent exerts a force on the object. It's down, and I've represented it with a vector, and my subscript R on B represents the force of the red ball on the blue square. This blue box is also an agent, and the red ball is also an object. The blue wall agent can exert a force on the red ball object, which I've represented here. So here I have a free body diagram for the red ball, and there's a force of the blue box on the red ball, and it's pointing up. And it's these two forces that are equal in magnitude and opposite in direction that represent a Newton's third law force pair. So that's going to be my working definition so far for Newton's third law. Newton's third law force pairs exist. They are equal in magnitude and opposite in direction. Now we have to be able to find them. In this video, there's going to be a series of questions I'm going to ask within the video that are key to being able to really understand how Newton's third law works. So the answer to the first question was no. They are not Newton's third law force pairs. Let's take a look. So we have a book on a table, and there are two forces acting on that book. There's the force of the table on the book, it points up, and there's a force due to gravity of the earth on the book, and that force is down. These forces are equal in magnitude, they are opposite directions, but they are not a Newton's third law force pair. Any two forces can be equal in magnitude and opposite in direction, but that doesn't necessarily make them a Newton's third law force pair. That brings us to the key point number one. The forces in a Newton's third law force pair cannot ever act on the same object. Here, both of the forces were acting on the book, which means they cannot be a Newton's third law force pair. And the answer to this is C. Both forces have the same magnitude. These forces are a Newton's third law force pair. Let's take a look. So I have this book falling, and I know that there's a force of gravity on the book. I've identified it with a free body diagram with a subscript E on B. So this is the force of the earth on the book. It's a gravitational force. Well, there's also a gravitational force of the book on the earth, and that's the Newton's third law force pair. It is equal in magnitude and opposite in direction. And at first glance, that may seem not right. It seems like the force that the Earth exerts on the book must be larger, but that's not true. It's the accelerations that are much different. Let's say we have a really large book, like a physics textbook, 10 kilograms. What sort of gravitational force is that? Well, in our force model, the force due to gravity is the mass times the acceleration due to gravity, which we're going to say is about 10 meters per second squared. And so that means that's a force of 100 newtons. The gravitational force the book exerts on the Earth is also 100 newtons. However, the mass of the Earth is about 6 times 10 to the 24 kilograms. So if we calculate the acceleration, we get about 2 times 10 to the negative 23 meters per second squared. The forces they exert on each other are the same, but the accelerations are so different, which is why you didn't see the Earth do anything. So that's the key point number 2. Just because the forces are the same does not mean the accelerations are the same. Just because the forces are the same does not mean the effects of the forces are the same. The answer to this question is E. Both forces exist and they have the same magnitude. These two are again a Newton's third law force pair. Let's take a look. So I have a small car of much smaller mass pushing a large truck. And so there's a force of the truck on the car, and it's pointing to the left, the subscript T on C for truck on the car. There's also a force of the car on the truck that is equal in magnitude, opposite in direction. These are a Newton's third law force pair. At which point you might ask, how does that work? How does the system accelerate if those forces are equal and opposite? So it's important to know that if you do a Newton's second law, you can only work on one object. So if you look at the truck, it's rolling along, and so there's a small frictional force of the Earth on the truck in the opposite direction. And the force of the car on the truck is larger than that, and so the system is accelerating to the right. Now the car is not in neutral, its transmission is engaged, and that creates a frictional force on the Earth, and then there's a frictional force that the Earth exerts on the car that is quite large. It's much larger than the force of the truck on the car, so the net force is also to the right, and that can create an acceleration. Now, if you've never looked at this before, you might be curious about how exactly that works with the friction on the ground. And that's a complicated story I'm not going to get into here. But the key point of this is the forces between the objects are a Newton's third law force pair, and they are equal in magnitude and opposite in direction. How can you find a Newton's third law force pair? Easy. Remember, every force can be written in the following way. The type of force on the object by the agent. For example, there is the contact force on the truck by the car, the gravitational force on the book by the Earth. To find the Newton's third law force pair, simply switch the objects of the prepositions. The contact force on the car by the truck is the Newton's third law force pair for the contact force on the truck by the car. The gravitational force on the Earth by the book is the Newton's third law force pair for the gravitational force on the book by the Earth. So as long as you construct these sentences, you will never get a Newton's third law force problem wrong again.